The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone and welcome to our second webinar on ExpressMarine. I'm Bruce Hayes, the Naval Architect for the Advanced Marine Technology Center in the U.S. We are the developers of the Orca 3D Marine Design plugin for Rhino, and we're the North American distributor of ExpressMarine and ShipWeight. For those of you who aren't familiar with the GoToWebinar interface, you can click on the orange arrow to minimize the control so you can see more of your screen. If you have questions during the webinar, you can type those into the question box. Because the demonstration today will be relatively detailed, we most likely will not have time to answer questions here in the webinar, but instead we'll assemble a summary of the submitted questions and the answers and distribute them in a follow-up email to everyone. We are recording today's webinar, and we'll include a link to the recording in the same email. So for the agenda today, we'll begin with some brief introductions, followed by an overview of ExpressMarine to help orient those of you who didn't attend the first webinar. Then we'll present a live demonstration, and finally we'll discuss the pricing options. The first of our panelists is Runar Osen of BAS Engineering in Norway. Runar is a naval architect and the managing director of BAS Engineering, and many of you know Runar is one of the developers of the ShipWeight mass properties software. Next is Yulu Prepelita. Yulu has a background in naval architecture and programming and worked several years for Rolls-Royce Marine as a structural engineer and in hydrodynamics before starting ExpressMarine. Okay, now I'll turn it over to Runar for an overview of the software, and then Yulu will follow with a live demonstration. So Runar, I'm going to make you the presenter. And as I said before, please feel free to type in questions during the webinar or send them to us by email afterwards.
Thank you, Bruce. I will now give a short introduction of the tool, a very brief overview using a few slides and a few minutes. So ExpressMarine, what is it? It's an algorithmic marine structure modeling plugin for Rhino. And the main objective of the tool is to get from a 3D hull surface combined with a 2D drawing to a 3D structure model in quote-unquote no time. The 3D hull surface can come from Orca 3D, it can be an IGES import, it can come from other tools as long as you can import it into Rhino. And the design drawing can of course be a CAD, a 2D CAD drawing from AutoCAD or similar tools. How do we get there in no time? To the 3D structure model. We get there by applying a structured and parametric modeling of the 3D marine structure, utilizing a 3-view that organizes the vessel into geographical and area-based logic. We have automatic creation of structure object based upon limits and references, and we have highly automated automation of repetitive tasks through mathematical algorithms. For example, you can define how to spread out a set of floors within the limits of the hull and the tank top, and also by applying stiffeners, cut-ups, outs, and openings definitions to these floors. When the objects are created, we have an associative topology both between the objects within the 3D models, which means that if you move a bulkhead, everything that's attached to the bulkhead follows, of course, and if you move a limit like the hull for the bulkhead also adjusts to that change in the limit. In addition, there's a link between the 3D object and the 2D representation on the drawing, which is also associative. This means that if you move a bulkhead on the 2D drawing, the 3D object in the 3D model also follows. The tree view that you saw also give a step-by-step driven process which guides you through the creation of the 3D structure. By starting with the hull, it starts by allowing you to first create the floors, girders, and the tank top and the decks, and then continues with webs, bulkheads, and so forth until the superstructure. And the results is 3D structure that is very good for early phase weight and central gravity that can be inputted to ship weight and used for weight calculations. It can also provide a starting point for a more detailed 3D model, and also it can provide a starting point for something you can mesh for FEM. So with that, I'll conclude this short introduction, and we should continue with the live demo.
Okay, thank you, Runar. And Yulu, I'm going to make you the presenter.
Thank you, Bruce, and hello, everybody. Thank you so much for joining this second webinar today. We will demonstrate you how to use ExpressMarine to model ship structures. If you see on my screen, this is the ship that we started modeling on the previous webinar, and this is the result that you could get if you spend some hours modeling. As you can see, this is a quite complex model, and this is what we call the phase one. So a complete model in phase one, where which is mostly used for weight and center of gravity assessment. And for today's webinar, we will apply on a 130-meter chemical tanker. And we're going to start from scratch and start building up the structure. So for that, we simply open Rhino. We don't need to use any templates. And simply type ExpressMarine create project. And then press enter. And you will see that the main parameter window will appear. We can give a name to this one. Let's call it demo tanker. Then we must fill all the other parameters and press apply. And you will see now that the main ExpressMarine window will open. As you can see, this is split in two. On the left side, we have the hierarchy where all the elements are being, where is the list with all the elements, all the structural elements, and on the right is the control panel where we set all the parameters. The main node in the tree is the top one called project, and it also contains the project name. And as you can see, it contains several tabs on the right. The first one is the main parameters, where you will see again the main data, so you can you are able to edit them at any time later if you need to alter your parameters. And you also have the possibility here to import the general arrangement drawing. And here is also where you can see the entire weight and center of gravity for the entire ship. The second tab is the framing system, and here you will be able to generate the grid for the ship. The second, the catalogs, where you can add some more materials. And we also have an export tab where you're able to export all the data, all the structure in a table format. Back to the tree. As you can see, the tree is divided into tiers, and what a tier is, it's simply a slice horizontal level through the ship. And depending on the number of decks, then the same number of tiers will be generated. And once you initiate an ExpressMarine project, then you will see that the first objects to appear will be these rectangles, and it's here where you will need to import your GA and place each deck section. And we now have the possibility to export these rectangles into AutoCAD as a DXF file, and then you can do all this preparation straight in AutoCAD, so that when you will import your drawings, then they will fall right into place. So also the way the structure is defined, you will see that each tier can contain specialized groups like the floors or the webs, or and each specialized group can also contain subgroups, and then in each subgroup the structural elements will be positioned, and every structural element is composed of plates and stiffeners. You will see later. Okay, so then we can start by importing the general arrangement. So we go in the main node, and then in main parameter, and then we just browse for the general arrangement drawing. So as you can see, I have arranged this in AutoCAD and export the DXF so that when I import it here in ExpressMarine, they will fall right into place. Okay, next would be to set the framing system. So we go and check the profile, and we see that the interval is 600 millimeters up to deck 10, up to frame 10, and then it changes to 700 millimeters all the way to 173, and then it changes back to 600 all the way forward. So we can fill this in the longitudinal framing system. The first delta was 600, and it went up to 10. Then it's 700 up to 173, frame 173, and then it switches back to 600. So now we set a frame string, and we press apply. And as you can see, frame scales have been defined in each of the rectangles. So we can maybe have a quick check in the profile if they coincide with what we brought from AutoCAD, from the GA. So that is okay. And now I think we're ready to start importing the shell. And because we're going to work with the symmetric shell, we need to go in the shell node and check that symmetric is active. Then we go in shell PS, and that will mean that all the editing that we do in this in the port side half of the shell will be reflected automatically to the starboard half. So we're ready now to import the hull surface by pressing browse. And as you can see, the hull surface has been imported into our project, and it is locked momentarily for a visual inspection. And if we confirm that this is the correct surface we want to work with, then we can go forward and trim the upper part of the hull so that we create a bulwark profile. For that, we have this function. We can pick the curve from the GA that defines the bulwark profile. We press this button, pick on GA, then we go in the profile selection box, and we pick the curve defining this bulwark profile. It must be a single polycurve. So if yours is split in more segments, you will need to join them. Now we go back in perspective view, and if we press the generate bulwark profile, then you will see that that curve has been extruded, so we can do a visual inspection if everything is okay. And now we can maybe change the thickness to 12 millimeters. We can leave the material as steel, maybe change the color to something lighter. And you see the limits are predefined to be y larger than 0 and the z smaller than this bulwark profile extrusion. So you can press apply. And this is the shell surface, which now has a weight and a center of gravity. It is a very good idea to save as much as possible, or as often as possible. And to do that, you simply use the save Rhino command. And I recommend you to give a name which is quite suggestive that it includes an ExpressMarine project. So something like chemical tanker and EM from ExpressMarine. Okay, so we notice that this shell doesn't contain a transom, so we can add it. This is a good opportunity to show you how to add some custom objects which are not predefined in this tree. So in the shell, we can right-click on the shell node and add a custom group, which we can rename to, let's say, shell custom elements. And now inside this custom group, we can add an X object. To tell you a bit more about this object, every structural object in ExpressMarine are defined based on the main orientation of the surface or the normal of the surface. And for example, a deck, because it's mainly a horizontal object, so it has the normal in the Z direction, we call that a Z object, or a transom, for example, or a transverse bulkhead, that would be an X object, or longitudinal bulkhead, that would be an Y object. So the transom is definitely an X object, and we can rename this custom X object we just added to transom. And we will define this on an X constant plane. But we know that this is at -3 meters. And the limits are in between y larger than shell SB, so between the shell surfaces. And I have measured previously, I know it should be not taller than 15.47. And if we apply, you'll see the transom was created. So the same principle will apply to any other types of objects you want to create which are not predefined in the tree. Okay, so I think now we're ready to add the deck. So we go in Tier 1, Deck 1 plane. And here I can show you that there are several modeling methods available, and this will be valid for all other types of objects. And the first modeling method, we can create the object on a flat plane. Here it's at a constant Z coordinate because this is a Z object, so a horizontal object. Or you can also pick from the general arrangement drawing a curve which will be then extruded into the 3D space. Or if you have predefined a surface, so if you obtain it from a different software, or if you receive it from the designers and so on, then you can import that surface right here and transform it into a structural object. Or there's also the possibility to model this surface right here in this project and then transform it into a structural object. So for this purpose, we will start with constant Z plane, and the tank top, let's say, is at 1.6 meters. And we just need to add some more limits. Just say that it's border on the starboard by the shell starboard and on port side by shell starboard port side. So we now we can apply, and this is the deck that has been created. But if we look into the profile, we see that the tank top is actually a knuckled surface. So we have a knuckle trace for it. So we have the possibility to use the second modeling method, pick on GA. So if we press this pick on GA button, then we choose this, we select this trace, which again must be one single continuous polysurface, polycurve. So again, we go in perspective, and if we reapply, you will now see that the tank top has been redefined with the shape that was defined in the general arrangement. Okay, so now maybe we can create some webs. We can start defining some floors, sorry, defining the structure of the double bottom. As you can see, the floors, the floor group can be further divided into more subgroups. And if you have some groups with similar parameters, properties, then it's a good idea to group them into more subgroups. And let's say we just add one more subgroup by right-clicking on the floor. Yes, and we can rename every group like we need. So let's say, for example, we can rename the first one to be midship floors. And now these subgroups, they have the possibility, they offer the possibility to generate multiple repetitive elements in one go. So we need to define at the modeling location, let's say every 3 frame spaces, and we'll start from, let's say, 40 up to frame 50. And we need to set the limits, for example, y larger than shell SB and less than shell PS. And the Z is predefined to be less than deck 1 plane, which is the tank top. So if we apply this, you will see that these floors were created in the double bottom area. So maybe what I should do, I should turn off the visibility of the deck 1 so that you can see better these floors. And now maybe I can choose one of these floors and do some more modeling. You could either click into the tree or you can click into the model to select one object. And you will see both of them will be selected in the same time. So maybe on this one, let's add some stiffeners. To do that, you go into this stiffener box and you press on the plus button. And you will find several available methods to create stiffeners, depending on the type of the object and the direction of the stiffeners. And let's say we add some vertical stiffeners on the next object, is that icon. We must give a name. Let's call it V1. And now we define them from, let's say, frame -20 to frame 20. Sorry, frame 20. And the spacing every frame, that means frame 1. And the profile, we choose a profile. Let's say we add a flat band. And you see, by default, the 100 times 10 millimeter is available, but you can go ahead and edit this into whatever dimension you need. So let's say 120 times 10. And you can confirm and apply. So here are the stiffeners created on this floor. But most of the stiffeners, they don't go all the way to the edges of the elements. So we have the possibility to edit this and add some offsets from the edge. So we can click on the edit button. And you see we have the upper border and an offset from that. We can choose the upper border to be the deck 1 plane, which is the tank top. And let's use a 200 millimeters offset from the edge. And the lower border, that could be the hull surface. And let's use a 200 millimeters as well from the edge, from the intersection with the hull. We can confirm it. And if we apply, you see now the stiffeners are smaller, and there's also a small offset, a small gap between the edge and the end of the stiffener. Now let's add maybe some openings onto this floor. In the cutouts and opening box, we could press the plus button. And again, we have various types of openings. We can have repetitive series of repetitive shapes of openings, or we can have openings that repeat in a certain direction, but with the height adapting to the contour of the element, or you can have a parametric offset where you offset all the edges of a certain element, or if we have some shapes defined already in the drawings, we can select those curves, those closed curves, and that shape will be then punched into the object. And for this one, maybe we could use a variable height manhole series. Is that icon, and we can give a name. Let's call it MH manholes, and we can define them from let's say from frame minus 17.5 to frame 17.5 every one frame. So the reason I've been using 17.5 is because I want the center of each opening to fall right in between stiffeners. And then we should also define the width of each opening, and let's say 400 millimeters. And now we need to tell it how far they should go to the edges of this element, or to the board, to a certain border. So for example, we could use as the upper border, that could be the deck 1 plane, the tank top, and with an offset of 200 millimeters. And from the sides, that can be the shell. So on the port side, we could use shell PS with the 300 offset. And from the starboard, that's the shell SB. Again, with a 300 millimeters offset. And we don't need to use anymore the lower border, because we know that the shell go all the way to the bottom. So I can confirm this and apply. So now you can see a series of variable height openings have been created, and they follow the contour of the shell. And this is how you can apply them all to all objects. Okay, maybe now we can turn on the visibility for deck 1 plane, and we can create the twin deck now, so that I can show you how to define some stiffeners onto a deck. So we go in tier 2 and deck 2 plane, and we know that this deck is at 7 meters, at a height of 7 meters, and the limits there, it should be defined between shell ports, starboard and shell port side, and on X that will be between the transom and frame 40. I have read this into the general arrangement. So we can apply to get the plate for the twin deck, and is that one there. And maybe I can show you how to add a seam. In the seam box, we can give a name to the first one. Let's call it seam 1. And let's say that we add a longitudinal seam, which runs parallel with the central line at a distance of 1 meter. So that would the format for that would be y equals 1. Just a second to change the keyboard. Okay. So y equals 1. And now if we apply, you will see that this object has been split in two. And then in the tree, we have two plates now. So we can go in each plate, and then we can set a separate thickness, material, color, and so on. And we can take the results for this from here. Now maybe we should add some stiffeners onto this deck. So we use again the plus button. And being a deck, we use the first type of stiffeners. We can give a name. Maybe we can call this longs, longitudinals. And we can define them, let's say from frame -20 to frame 20. It is okay even if you define them outside the shell, if they won't be, so even if you define them outside the actual borders of the element, if an intersection is not found at that position, then it's okay. It will just, it will only create where it will find a possible position. So the spacing, let's create them at every frame. And in preparation for the addition of some longitudinal beams, we should also add some exceptions. And let's say in the exception box, we can say that do not create every 4. So we make a mini series, and this is the format. Every 4 from frame, let's say -12 to frame 12. And we should choose also a profile from this list. And let's say we add an HP profile. Now we can confirm, and we can apply. And as you can see, the stiffeners have been created under the deck, and we have some blank spaces where we will further create the longitudinal beams. So we use again the plus button, and we will add again some longitudinals. This time we could call them LW, longitudinal webs, let's say. And we will define them in the same position where we define the exceptions for the previous definition. So that would be from frame -12 up to frame 12, every 4 frame spaces. And the profile, that would be, we can pick, for example, a T profile, a T beam, and you see this is the format of it. You can select the default one, and you can then modify it as you wish. Let's say the 400, we can switch it to a 450, and so on. And then you apply, you confirm, and then apply. And then you see the beams, longitudinal beams were created. And let's now add some transverse beams as well. And that is the symbol for it. We call them TWs. And let's say we start them from X frame -4 to X frame 36. And the spacing will be every 4 frames. Now the profile, I can choose again a T profile, can confirm and apply. So here is how you can define all the stiffeners under a deck. Okay, I want to show you how to define some bulkheads, and for that we will need to generate also the third deck, the main deck. So we go in deck 3 plane, and just let's simply make this on a flat plane at 11 meters, and set the limits to be again x larger than the transom, and then y larger than shell SB and shell PS, and we can apply it. But I will, so this is the result, but I will turn the visibility for it off so that you can see the bulkheads inside better. For bulkheads, we have a quick method of defining them, where if you have them available onto the general arrangement drawing, then you can simply pick them from there, and we will extrude them up in between the limits that you define. So if we go in deck 3, in tier 3 bulkheads node, then you see we have on the modeling location, we have the possibility to pick the traces. Now this box is empty, and now if we press the button pick traces, and then we go into the general arrangement on deck 2. Now we can select this. Let's say we will use all the corrugated bulkheads. And the longitudinal one, and maybe I should also pick the first and the last from the cargo area. And now we can press enter, and you see this traces box. It has been populated with all the traces that we picked, and they will later become the bulkheads. If we go back to the perspective view, and so if we go in the node, in the bulkheads node, okay, here is where we should define the limits. And the limit by default, because we are in tier 3, we are suggested to use from deck 2 to deck 3, but this is a special case where the this cargo area bulkheads, they go from deck 1 plane up to deck 3, so from the tank top to the main deck. So we switch that to deck 1 plane, and we can simply apply. So you see, this is how they are being added into the model. And as you can see, some of the bulkheads, they go outside the shell. And for that, to fix that, we can just select one of those that have this. And it was because we needed to add some more limits for them. So that would be y larger than shell SB and less than shell PS. And if we apply, then it will be cut to the correct size. And as you can see, by accident, I have dragged the surface of the transom, but that is okay. If you just select it, and if you will apply again, it will be redefined to the correct space. Okay, so maybe I can also show you how to define some stiffeners onto the shell. So we go in shell PS, and we press the plus button, and we choose these side vertical stiffeners. And now we give a name. Let's call them frames. And the X start, that would be from frame 41 up to frame 172, let's say. That's the cargo area. And the spacing would be 1 frame, frame 1. The profile, we can choose any HP profile. And the upper limit, let's use the main deck, which is deck 3 plane. We can simply leave blank the upper offset so that it will go right onto main deck, and they can start right from the tank top. That would be on the lower border. We will simply choose deck 1 plane. So if we confirm this and apply, this may take a bit. Okay, so now you see we have obtained a series of stiffeners, vertical stiffeners onto the shell. And if you wanted that some of them not to be created where, for example, a web will pass, or where a watertight bulkhead will pass, you should have simply added that in the exception. So you can add those positions into the exceptions. Okay, so I'll cancel this. Next, I can show you how to define some openings onto the shell. And we saw in the GA that in the aft area there are some big cutouts some large cutouts. So we can, because they are already drawn here, we have two possibilities. We can add a series of rectangles with those dimensions, but since we already have them defined here on the drawing, you can simply add a pick trace cutout. And we use this one, and you will see this small pop-up window will appear. We'll give a name here. Let's call them O1, openings 1. And use the pick button. And now we simply select from the profile these curves. And for example, if you will need to unselect some of them, just like Rhino does, you simply press Control and click on it again, and it will be deselected. But I'll select it back. So press Enter when you're ready. And now confirm. And if we go back in the 3D view, we can apply. And you see those cutouts have been defined into the shell. So yeah, this is basically the general method of how to create all sorts of elements. Depending on how much time you will spend, you can go very much into details, and instead of creating very large groups of repetitive elements, you can create smaller groups, so with less elements, but you could define more details in them so that the structure will be more and more precise. This we're gonna use this this ship, and we're gonna make a tutorial out of it, and it will be available very soon. We already have on our website a tutorial, but that was created in the previous version. But an update will come very soon, and we will send you a message when that is ready. And okay, now maybe I will give the word to Runar. He will talk a bit about the pricing model. Thank you so much.
Okay, thank you, Yulu. Let me make Runar the presenter again.
Yeah, thank you, Bruce. So first of all, where can you find the price? If you go to our website, ExpressMarine3D.com, from the home screen here, you will find a button that says Buy. And if you click on the Buy button, you will find the pricing information. So to find out what you will have to pay, you have to ask yourself a couple of questions. The first question is, do you need the Pro version or the small craft version? The Pro version is has no limitations on the size of the vessel, while the small craft version is limited to 24 meters in length and 3 decks. When you know which version you want, you have to ask yourself if you need a standalone version or a network version. And finally, when you know that, you have the options of doing a perpetual license with an optional annual maintenance and support agreement, or if you want to do a subscription type of licensing. So, for example, the small craft subscription version on a standalone computer would be sort of the starting point of 750 euros per year, while the perpetual standalone is 950 euros for that small craft version. And the Pro version comes in a network as well, which is 25% higher than a standalone. So a network version means that you can install the software on any number of machines, but the number of licenses that determines how many machines can use the software at the same time. While the standalone license, that applies only to the machine where it is installed. I think that sums up the, I hope that sums up and answers your questions about pricing. The details and the values and the numbers you can find again on our website, expressmarine3d.com. So,
okay, thank you, Runar. I'm going to take back control here. So, Yulu, could you just say a few words about downloading and running the evaluation version?
Yes, thank you, Bruce. On our website, if you can please switch to my screen, Bruce. On our website, you will be able to download a free version, a trial version, which you will be able to use for 30 days. And we will actually recommend you that before you try, if you want, you can request us to offer you a live demo online, and we will be very happy to show you how ExpressMarine can be applied to your specific type of ships. And then you can simply download the version 1.2 and try it. And if later you will need need an extension of this trial period, please feel free to contact us and we will help you with that. Thank you.
Okay, very good. Thank you, Yulu. I'm going to make myself the presenter again here quickly. And just as a reminder, with any questions, we have a few questions here that we'll summarize in a follow-up email along with a link to the recording. And of course, if you have any other questions that you think of later on, please feel free to send those to us at support@expressmarine3d.com. And as Runar and Yulu have said, there's lots of information on the website, expressmarine3d.com. Okay, I think that's a good point to wrap things up. As I said, we'll be sending out a follow-up email with some information, and we hope you'll take the time to download and try ExpressMarine and contact us with any questions. On behalf of Runar, Yulu, and myself, thank you very much for your time, and goodbye.